Imagine building a scientific observatory in a place where winter temperatures drop to minus 80 degrees Celsius, where you're 929 kilometers from the nearest human being, and where the sun doesn't rise for months at a time. Now imagine that observatory has to run completely on its own for 51 weeks of the year, with no human intervention whatsoever. This isn't science fiction, this is Plato R, the most extreme observatory on Earth, built in one of the most hostile environments our planet has to offer, and the engineering behind it will blow your mind. Today, we're heading to Ridge A in Antarctica, a place so remote and so brutal that it makes the International Space Station look like a cozy vacation spot. Here, at 81 degrees 40 minutes 24.8 seconds south, 72 degrees 42 minutes 58 seconds east, sits an engineering marvel that's rewriting the rules of what's possible in extreme environments. Plato R isn't just any observatory, it's an autonomous robotic system that operates year-round in conditions that would kill a human in minutes. We're talking about the coldest, driest, and calmest site on the planet, a place where the air is so thin you'd need an oxygen mask just to breathe. We're talking about altitudes where even experienced mountaineers struggle to survive, and where the nearest human contact is nearly 1,000 kilometers away. But here's what makes this story incredible. The engineering challenges they had to solve weren't just about surviving Antarctica. They had to create a system that could generate its own power, maintain its own temperature, communicate with the outside world, and conduct cutting-edge astronomy research, all while operating like a spacecraft, but on Earth. This project is a collaboration between the University of Arizona in the USA and the University of New South Wales in Australia, with support from organizations like the US National Science Foundation. So how do you build something that can survive in hell and still do world-class science? Let's find out. To understand why Plato R is such an engineering marvel, you first need to understand where it operates. Ridge A isn't just cold, it's a place that redefines what extreme means. Picture this, you're standing at an elevation of 4,035 meters, which already puts you in the death zone for most humans. The atmospheric pressure is so low that it's equivalent to being at 4,650 meters. That's higher than most people can survive without supplemental oxygen. But the altitude is just the beginning. Winter temperatures here regularly drop below minus 70 degrees Celsius and can even reach minus 80 degrees Celsius or lower. That's cold enough to freeze carbon dioxide out of the air in extreme cases. It's so cold that if you breathe the air directly, it could lead to rapid hypothermia. The wind, it's virtually non-existent, which sounds good until you realize that means there's no natural mixing of the air. The atmosphere becomes stratified in layers, creating some of the most stable air conditions on Earth. And here's the kicker, there's almost no water vapor in the air. We're talking about humidity levels that make the Sahara Desert look tropical. Now you might be thinking, why would anyone want to build anything in such a hellish place? And that's exactly what makes Ridge A perfect for astronomy. You see, all those conditions that make it impossible for humans to survive make it absolutely perfect for telescopes. The lack of water vapor means you can observe in terahertz frequencies that are completely blocked everywhere else on Earth. The stable air means no atmospheric turbulence to blur your images, and the isolation means no light pollution for thousands of kilometers in any direction. Site testing has confirmed Ridge A's superior conditions for astronomy, making it the ideal spot for this kind of work. But there's one massive problem. How do you build and operate sophisticated scientific equipment in a place where humans can only survive for a few weeks at a time, and only during the brief Antarctic summer? The challenge facing the Plato R team wasn't just about building equipment that could survive Antarctica. They had to create something that could think for itself. Consider this, for 51 weeks out of every year, Plato R operates with zero human intervention, no technicians to fix problems, no engineers to adjust settings, no one to refuel generators or clear ice from equipment. The nearest humans are at the South Pole Station, 929 kilometers away, and even they can't help during the brutal Antarctic winter. This meant the engineers had to solve problems that had never been solved before. How do you generate power when solar panels are useless for months at a time? How do you keep sensitive electronics warm when the outside temperature could freeze steel? How do you communicate with the outside world when you're in one of the most remote locations on Earth? And here's what makes it even more challenging. Everything had to be transported to Ridge A by aircraft. We're not talking about building a road or shipping containers by sea. Every single component had to be light enough and small enough to fit in a Twin Otter aircraft, one of the few planes capable of landing on the Antarctic plateau. The solution they came up with was revolutionary. Instead of building a traditional observatory, they essentially built a spacecraft that operates on the ground. Plato R functions like a satellite with its own power generation, thermal management, communication systems, and autonomous operation, except it's sitting on the most hostile continent on Earth. But the real genius was in the modular design. The entire system consists of just two lightweight fiberglass modules, each weighing around 500 kilograms. One module houses the power generation system, the other contains the scientific instruments and computers. Simple in concept, but the engineering inside each module is absolutely mind-blowing. The modules are connected by a 120-volt DC cable for power distribution and a CAN bus for control. Let's start with the most critical challenge: power. In a place where temperatures regularly drop to minus 70 degrees Celsius, where there's no sunlight for months, and where fuel delivery is impossible for most of the year, how do you keep a sophisticated observatory running? The Plato R team came up with a hybrid solution that's pure engineering genius. First, they installed two HATS 1B30 diesel engines in the engine module. These aren't your typical generators, they're specially modified to operate in extreme cold. The system carries 800 liters of AN8 fuel, which is a special Arctic-grade diesel that won't freeze even at minus 70 degrees Celsius. But here's the clever part: they don't run the engines continuously. That would waste fuel and create unnecessary wear. Instead, the engines only kick in when the battery bank gets low or when the scientific instruments need extra power. The 120-volt DC system distributes up to 3 kilowatts of power. For the rest of the time, Plato R relies on solar power. Now you might be thinking, solar power in Antarctica during the polar night? But remember, Antarctica has a summer too. During the brief Antarctic summer, the sun never sets. It just circles around the sky 24 hours a day. The solar array consists of 8 195-watt panels arranged in a cube configuration. This unusual setup isn't just for looks, it's designed to capture sunlight from any angle as the sun moves around the sky. During peak summer conditions, the solar array can generate 0.9 kilowatts of power, which is enough to run the entire observatory. The result? During the Antarctic summer, Plato R operates entirely on solar power for months at a time. During winter, the diesel engines provide reliable power while consuming fuel at a rate that allows the system to operate for an entire year between refueling visits. But generating power is only half the battle. The real challenge is managing that power in extreme conditions. Keeping electronics warm in minus 70 degrees Celsius temperatures isn't just difficult, it's a constant battle against the laws of physics. Heat wants to escape, and in Antarctica, it escapes fast. The Plato R engineers solved this with a multi-layered approach that would make NASA proud. First, both modules are heavily insulated with specialized materials designed for extreme cold. But insulation alone isn't enough when you're dealing with temperature differences of over 90 degrees Celsius between the inside and outside of the modules. The real genius is in the waste heat recovery system. Remember those diesel engines? When they run, they generate a lot of waste heat. Instead of letting that heat escape into the Antarctic air, Plato R captures it and uses it to warm the modules. It's like having a built-in heating system that runs on the same fuel that powers the generators. But what about when the engines aren't running? That's where the thermal mass comes in. The modules are designed to store heat like a giant thermal battery. The computers, electronics, and even the battery bank all generate small amounts of heat, and the insulation system is so effective that this heat is enough to keep the interior temperature stable. The system is so well designed that the interior of the modules stays warm enough for sensitive electronics to operate normally, even when the outside temperature is cold enough to freeze the air itself. And here's a detail that shows just how thoroughly the engineers thought this through. The modules are connected by a 120-volt DC cable that not only carries power but also allows heat to be shared between the two modules. If one module gets too cold, it can draw heat from the other. It's like the modules are looking out for each other. The modules are positioned about 60 meters apart to minimize vibration and other interference risks. Now imagine trying to send an email from a place that's 929 kilometers from the nearest human being, where there are no cell towers, no internet cables, and no communication infrastructure of any kind. How do you stay in touch with the outside world? Plato R's solution is both elegant and sophisticated: Iridium satellite communication with redundant modems for reliability. The Iridium satellite constellation is one of the few communication systems that provides truly global coverage, including the polar regions. Plato R is equipped with Iridium satellite modems that can transmit data anywhere on Earth, even from the most remote location on the planet. But here's the challenge. Satellite communication is expensive and slow. The system can only transmit about 20 megabytes of data per day. That might sound like a lot, but when you're running sophisticated scientific instruments that generate massive amounts of data, 20 megabytes is practically nothing. So the engineers had to get creative. Plato R doesn't just dump raw data to the satellites. Instead, it processes the data locally, compresses it, and only transmits the most important results. The system is smart enough to prioritize critical data and queue less important information for transmission when bandwidth is available. The result is that scientists around the world can monitor Plato R's operations in real time, receive scientific data within hours of it being collected, and even send commands to adjust the observatory's operations, all from a location that's more isolated than the International Space Station. At the heart of Plato R's autonomous operation is a computer system that has to be smarter than most spacecraft. Remember, this system has to make decisions on its own for 51 weeks of the year, with no human intervention. The control system uses redundant PC/104 computers running Debian GNU/Linux on flash disks with a read-only file system for added reliability. These aren't your typical desktop computers. They're ruggedized systems designed for extreme environments and tested for high altitude and low temperature reliability. But the real intelligence is in the software. Plato R's control system constantly monitors every aspect of the observatory's operation. It tracks power generation and consumption, monitors temperatures throughout both modules, manages the scientific instruments, and handles all communication with the outside world. The system is programmed with decision trees for virtually every situation it might encounter. If the temperature drops too low, it knows to start the diesel engines. If a scientific instrument malfunctions, it knows to switch to backup systems. If the satellite communication fails, it knows to store data locally and retry transmission later. And here's what makes it truly remarkable. The system optimizes from experience. It tracks patterns in power consumption, weather conditions, and equipment performance, and uses this data to refine its rule-based operations over time. The result is an observatory that doesn't just survive in Antarctica, it thrives there, conducting world-class science with a level of autonomy that rivals the most sophisticated space missions. So what makes all this incredible engineering worth it? The science that Plato R enables is literally impossible anywhere else on Earth. The observatory's primary instrument is the HEAT telescope, a 0.6-meter aperture telescope that observes in terahertz frequencies. These are wavelengths that are completely blocked by water vapor in the atmosphere, which means they can only be observed from space or from the ultra-dry conditions of Ridge A. HEAT is mapping the Milky Way's interstellar medium, studying the forms of carbon that exist between the stars. This research is helping us understand how stars form and how the galaxy evolves over time. The telescope has already identified a giant gas cloud that's likely to form a star cluster similar to Orion and provided evidence that there's 50% more star-forming gas in our galaxy than we previously thought. Data releases like DR1 in 2014 and DR2 in 2015 have shared maps and spectra from these observations. But Plato R isn't just about astronomy. The observatory also monitors atmospheric conditions, tracks climate data, and serves as a testbed for extreme environment technologies. The engineering solutions developed for Plato R are being applied to everything from Mars rovers to Arctic research stations. Since it began operations in 2012, Plato R has operated continuously, generating scientific data that's advancing our understanding of both our galaxy and our planet. It's proof that with enough engineering ingenuity, humans can build systems that operate successfully in the most extreme environments imaginable. Plato R represents something truly special in the world of engineering. It's not just a telescope or a weather station, it's a demonstration of what's possible when brilliant engineers are given an impossible challenge. In a place where humans can barely survive, where the conditions are more hostile than most of outer space, a small team of engineers built a system that operates autonomously for years at a time, conducts world-class science, and pushes the boundaries of what we thought was possible. The next time you think an engineering challenge is impossible, remember Plato R. Remember that somewhere in Antarctica, right now, a small robotic observatory is quietly revolutionizing our understanding of the universe, powered by nothing but human ingenuity and some truly incredible engineering. And that's the story of how engineers built a spacecraft that operates on Earth, in the most extreme location our planet has to offer. If you enjoyed this video, hit that like button, drop a comment with your thoughts, and don't forget to subscribe for more mega builds.